Professor Angela Rasmussen from the Department of Electrical and Computer Engineering at the University of Utah, and I'm going to go over a BJT example. And so this is going to be the circuit that we're going to look at. In this, you would solve this circuit using the DC analysis for an active mode conditions, and you would take a Thevenin of this more complicated circuit here. And what you're going to find, and I'll leave this as an exercise to do, is that you will find that the Thevenin voltage, VTH here, is going to be 3 volts and RTH will be 5K. From using those values, you're going to be able to solve this to get IC, IB, and IE, and then the voltages VC, VB, and VE. So solving that, you should find, write them up here, that IE is 1.8 milli, IB is 17.8 micro, and IC is 1.78 milli. And then you will also find that VB is 2.9 volts, VE is 2.2 volts, and VC is 3.2 volts. So seeing that VB and VC is, there's 3.2 is greater than 2.9 verifies that this is in the active mode. So that would be the proof that VC is greater than VB. And 3.2 is greater than 2.9, yes. So true. So this would be the DC answers. Again, this is going to be an exercise to go and use. So you can pause this, go find those. What I want to talk about is the second part of this problem, which is what is the maximum amplitude for this input source. Once I have designed this amplifier, gotten it to work in the active mode, my conditions are met, but now I'm going to have some limitations on what input I can actually put onto this and still amplify. So this amplification is at the collector side. So collector versus this input of V8 is found to be a minus 2 volts per volt. This means that I plugged in the hybrid pi for this circuit, analyzed that, short-circuited all of the capacitors in here. So this one was shorted to solve for that amplification, and I get that one value. That means that as long as it's in its operating region, I should get a minus 2 volts per volt for whatever input. If I put 1 volt in, I should get minus 2 volts out as an amplitude. So what happens if I do that is that if my output is taken at VC, and why that's doing that, there we go. That just kind of messed up all of my, very strange. Okay. Okay, now I think it's back. All right, let's see if yep, I can draw on it. Okay, if my DC value of VC is 3.2, if my input is 1 volt amplitude, and I have the gain of minus 2, that means that this output is going to go up to 5.2 volts. And I look at this and say, well, is that even possible? I have a limitation here of the maximum out that I could get is my supply voltage. So it can't go higher than 5 volts. So a 1.2 volt input is going to be too high of an input because I'm going to hit that rail of 5 volts, and then it will just go flat at 5 volts. It can't go above 5 volts. So there's going to be limitation due to that supply voltage. And then the other one is, say it goes down by 2 volts to a 1.2, well, that would be less than the DC value of 2.9. So I'm also having a limitation between my VC and VB. So there's going to be a limitation there and a limitation on the maximum output I can do from this power supply. So I need to look at both of those and see which one is more constrictive and say that would limit my input to be that value. So let's first look at the rail voltage of 5 volts. So knowing that it can't go higher than 5 volts, that means that between 5 volts and 3.2, that difference is going to be 1.8 volts. So 1.8 volts there, and if VC, between VC, so this is due to supply voltage. And then if I'm looking at between VC to VB, then that difference is from 3.2 to 2.9. That's only a 0.3 volts. Well, you can see, well, this one at 0.3 is definitely going to be much more limiting because it's a smaller value. So my input then will be limited if my input, so we know the gain, VC over V8 is that minus 2 volts per volt. And remember here, the minus sign just means that it's inverting it. It's going to just take, if it's in positive input, it's going to make it a negative output. So we can ignore the negatives, and we're looking at more the gain portion, which is just the magnitude of 2 here. So if I limit this output in AC to only be a 0.3 volt difference, and I solve this, then my input here is going to be 0.3 over 2. So the maximum it would be 0.15 volt input. So looking at this, so say I put in a 0.1 amplitude, which is less than the 0.15, and it goes up and down, and it's going to go down to a minus 0.1. My output then, when this is a positive, will be negative, and it will amplify it by 2. So it will go down to a minus 0.2, and it will go up to a plus 0.2. So when it's a positive peak there, it's going to be a negative peak. And when it's a negative peak, it's going to be the positive peak. So it will look like this in your output. And it never goes, and so this is added on again to that DC value of 3.2. So this is only looking at the AC only. So this will actually be 3.2, and if I add on the 1, this value would be 3.3. This value would be 3.1, and going up, this would be 3.4, and then going down would be 3.0. So you can see that it never reaches the value of the DC value of 2.9, and it never goes higher than the 5 volts. So this would amplify it what's called linearly, so it doesn't cut it off or distort it in any portion of this. All right, that was this example. Thanks for watching.